Coming to the next topic, that is buoyancy. So this topic is very interesting in fluid statics syllabus. So all of you know the Archimedes principle that whenever a body is floating or submerged or just try to immerse in the liquid, it will experience some resistance force or some lifting force. So whenever we also walk in normal atmosphere, we can feel our weight, which is higher than whenever we are in the water or any high density fluids. Our weight will be felt very less. So similarly here, if you take different bodies, so when a body is completely or partially immersed in a fluid, the hydrostatic lift, so whatever the lift or the resistance force is acting, to the net vertical component of hydrostatic pressure force means whatever the weight of the body is there, which is tried to submerge inside the liquid, it will experience same vertical opposite direction in the upward direction in the same hydrostatic lift or the same hydrostatic weight force. So these two vertical forces what are experienced is called the buoyant force, and the phenomena is also called buoyancy. So some books have called buoyancy or some books have called buoyant force. So force is buoyant force. This phenomena of lifting the body, floating or submerging the bodies is called buoyancy phenomena. Now coming to the details of this topic, you can see here a small non-uniform body is taken like a stone, and here we are trying to show the total weight of this body, that is mass into gravitational force. The total weight of this body is acting in the downward direction. Just for notation, we have shown it upward. It may be downside also can be shown, but weight of the body always trying to act in the downward direction. Now this buoyancy force or the force which is registered by the fluids which are having high density than the air or higher density compared to our atmosphere. So in such conditions, whatever this force is acting in the upward direction or resisting the submerging of the bodies, that force is exactly opposite and vertically upwards in the same line of the weight. So this force is called as buoyancy force. So all might have seen any surface or the given material, if you try to dip in water, some bodies will float, some bodies will completely sink into the water. So this is due to its density, and this phenomena is called as Archimedes principle or the buoyancy can call. So this upward force exerted by the fluid is also equal to, this is very important for entire topic of buoyancy, because all the numericals if you consider, you have to consider this force which is equal to the weight of the fluid displaced by that body. If you remember this sentence, the numericals and the topic of buoyancy is completed today itself. Means what? Whatever the volume of this unknown volume you have taken, this body, whenever it completely submerged inside the liquid, just suspended or completely sinked inside the water, or in the floating conditions. In this example, if you see, water surface is shown in the red line, and partly this stone is partly submerged, and part of the stone is above the liquid surface. It is in the air. So some volume of air is replaced by the stone, and this partial volume of the stone, what is replaced by the liquid volume. Okay, so this volume, whatever is replaced by the liquid volume, that volume is stored by the or sustained by this stone itself. So like this, we are taking the force of buoyancy, what is exerted on any body, it may be a solid or whatever, the force, magnitude of that force, we are going to make it equalize or take to equal to the weight of that fluid displaced by that body. So how much volume of fluid is displaced here from the red line to this volume of the stone, that weight of the fluid or the water, if you consider general fluid as water, that weight of water, how much it is displaced by the stone, if it is partially immersed, that volume or the weight of the fluid is equal to this force. So that indicates what? The upward force or the resisting force to the weight. Okay, it is nothing but the force exerted by the fluid is also equal. That buoyancy force is also equal to the weight of that volume of the fluid displaced. So that volume is what? Here we have not considered any standard volume. We have taken just a reference, just an example, irregular volume. Any shape of the stone or any shape of the body we have taken, just to analyze, to understand how much is the force applied. How much is the force applied means the volume, how much it is immersed. If it is completely immersed inside the liquid, total volume of the stone, if you consider, the total volume of the stone is replaced by what? Or volume of liquid is replaced by the stone. So if it is completely sinked or completely kept immersed in the liquid, then you have to consider total volume. Total volume of the liquid, what is replaced by the that weight of the liquid, if you that weight of the liquid is equal to this buoyancy force. And weight of the, if you see, that will be different. If the body is less than the buoyancy force, then it will float. So that everyone can understand. Weight of the body is less than buoyancy force, then body will float. The weight of the body is exactly equal to the buoyancy force. It may just touch the surface, means just submerge to the surface, and it cannot completely submerge or completely sink also. It may suspend or float inside the submerged body also. That depends. And if the weight of any body is more than this buoyancy force, it will sink. The points are clear. So all you should know to remember is whatever the given volume of solid body is immersed. So we'll assume solid body. Any solid body, when it is immersed in liquid, whatever the volume it is replacing with the liquid, that volume of liquid, okay, for that how much weight is there, that much weight or that much resisting force is acting in the vertically opposite direction to the weight. If it is more, the body will float. If the opposing force is equal, then it will just float on the surface or it will just submerge in the liquid. Means the point of weight what I have shown here, arrow mark is shown, that will be just aligned with the free surface of water when the weight of the body is equal to weight of that buoyancy force. Okay, next we'll take that center of buoyancy will be the center of fluid displaced. So many times we talk about the center of weight for the given body, center of the buoyancy force, because earlier hydrostatic forces when we discussed, we also discussed about the location of that force. So here also whenever the buoyancy force is acting, so where is that point located in the vertical line? That also we are going to find out. But here, if any body is floating, because in the fluid mechanics, we are maximum times in this buoyancy, we are focusing on floating bodies like a ship. The ship which is floating in the given sea, it is having, it can sustain the weight, but it cannot sink. So like that it is designed. In such cases, where this buoyancy point is located or the buoyancy force point is located, that is very important. If the buoyancy force is located just below the center of that volume of the given solid body, then it will be a stable body. It will float always. And whenever this buoyancy force point, if it is just above the center of that volume of the solid body, then it may sink. So that depends on the given location. So here, if the buoyancy force is just below the center of this volume of the given solid body, means that buoyancy center point is whatever the volume of liquid is replaced. No, say for example, some ship is just placed in the given lake, so some water or the volume of water will be replaced. I hope you are understanding. So whatever the volume of water is replaced due to that partly submerged body, that center of volume of water, if you consider, that is the center of buoyancy force. So that volume you should find out. Volume of the liquid, if you find out, center of that volume is the buoyancy force point. If you find out the volume of the solid body which is floating or sinking or just touching the free surface, such solid bodies, if you take the center, that will become the weight or the center of the weight or the center of the volume of solid surface. So that is explained in these sketches. So whenever a free surface or the floating surface is there, so this is a free surface of water considered here. When a floating body is there, see the buoyancy force. It is acting vertically upward direction. So this buoyancy force is acting because of the water here or the higher density liquid which is placed below. This may be considered as atmosphere at the top. So weight is acting downwards, buoyancy force is acting upwards. Now if you see, the weight of the given solid body may be concentrated at this point, volume center of the stone, for example. Now, center of the buoyancy point or the location of the buoyancy point, if you want to find out, what I'm doing, I'm taking the volume of liquids replaced. See, here, liquid is partly just below the surface of the stone. From this surface, whatever the volume is there, see the volume, it is in 3D, not in 2D. So three-dimensional, whatever the volume, if you consider this volume, whatever the water is replaced, that center if you take, the liquid volume center itself is the buoyancy point. So as I told you, if the buoyancy point and the center of solid both are at same point, or if the weight is just equal to buoyancy force, or weight is more than the buoyancy force, that solid body may be sinking in the given liquid. So in such conditions, the liquid, whatever is replaced, that liquid center, if you see, that is exactly at the center of the given solid body here. That is one thing for the given uh, sinking bodies or the suspended bodies. And if the body is completely sinking inside, so that buoyancy force, if you see buoyancy point, it may be little bit above the center of the volume of the given solid. So in such cases, the body may be suspended or it may be completely sinking in the liquid. So that weight should be less compared to the force of the buoyancy. Then only it can float. So that principle you have to achieve. Now we'll just observe how to find out that location of center of buoyancy, how it is exactly equal to the volume of liquid itself, or exactly center of the liquid volume itself. Or it can also, I am trying to call it as location of center of buoyancy or weight of the liquid. Why? Because weight of the liquid center also, if you take, it is nothing but the buoyancy point as per the buoyancy principle. So I can call it as location of center of buoyancy. That center of buoyancy point, what you find out, is nothing but what? The total center of the total volume of the liquid replaced location. If you want to go for magnitude, how much it is acting, then I will tell it the buoyancy force what is acting, which is more than the weight of the ship also. For example, if the ship is floating, then buoyancy force always it is a more than the weight of the ship. Then only it is floating. So for that condition, what I will tell, the magnitude of the buoyancy force is nothing but the total weight of the liquid what it is replaced by the ship body. Okay. So coming to this analysis, it's a simple analysis, but they have taken one sketch here how it is volume of the liquid. So this sketch you can just observe. They have taken one irregular shape named as ABCD. So ABCD, you can assume one stone is put inside water, and it is suspended in liquid. So that stone is such that it can suspend. It cannot sink to the bottom. It cannot come to the or above the free surface of water also. It is just moving freely inside the water itself. Means what I'm telling, I'm trying to tell the point of buoyancy and the weight or the center of the solid body, both are same. Both are at the same point. Then it will be suspending inside the liquid. So that type of body is considered ABCD body. Suspended in liquid of specific weight W, and they have taken two volumes here from the vertical line. They have taken two volumes. That is, one volume is upper side of this stone. If you see, that is A, B, C, and 2 points they have taken EF at the free surface of water. So this volume, if you see, it is upper volume is ADCFE. Okay, that they have taken ADCFE, one volume at the top side. So due to which the weight is acting in the downward direction. So that force, the total force acting due to this volume, upper side volume ADCFE, they have taken as F1. One more volume what they have considered is total volume. Total volume is from the free surface of water. Total volume is A, B, C, F, E. The volume of liquid, total volume of the stone also, or the irregular body also. Both they have taken. That volume, because of this volume, whatever the force is acting, okay, that they have considered F2. So that weight into this volume ABCFE, ABCFE. Or you can assume that the stone is tied with a string or any wire, and that wire may be applied with some F2 force, total force, up to this point, up to this suspended point. In such condition, what may be the total weight or the total force required to keep this body in a given position? So one of the upper volume is this part, and total volume is ABCFE. And anyone can tell the remaining volume is what? If I take the difference between F2 and F1, see, F2 is total volume AB with stone, ABCFE with stone. F1 force, if you see, because of the liquid volume, that is ADCFE. If I take F2 minus F1, I'll be getting again the stone volume itself. So that stone volume they have taken here. So net vertical force exerted by the liquid on the body, okay, is nothing but the buoyancy force only. That only we need to find out. So that can be found out how? Because it is suspended, it may be moving in given liquid volume. So at a given position, as per this sketch what you have considered, I can take the difference between F2 and F2, the force due to weight of the stone, okay, and force due to weight of the liquid above that stone which is acting. Both are adding here, and the buoyancy force should overcome, or it may be equal. If it is equal, the stone will be remaining at this position only, in this position only, always, because the weight of the liquid at this point in vertical direction and weight of this given solid stone, both will be acting downside, and to balance the stone at a given position, equal buoyancy force should also act. Then only it will balance. Otherwise, it may sink or it may float. Again, it may go back to upper free surface and it may start floating if the buoyancy force is more. If buoyancy force is equal to the total weight of the stone as well as liquid, which is above here, the hydrostatic force, if both are equal, then only it can be suspended at a given position. So that condition they have assumed. So that's how what they have written. Buoyancy force is equal to sum of this F2 plus F1, and we can also consider the difference to find the stone, the force due to stone, how much it is acting. So to take the force or the weight, whatever is acting downside direction because of the stone only, then you take F2 minus F1. All of you are understanding? Yes. Is buoyancy force decrease or increase downside direction? Yes. As you move downside, the buoyancy force may be little bit higher, because at the surface, if you see, partly the body is immersed. Say for example, half of the volume of the body is immersed. So only that much volume of liquid is displaced. And due to the weight of that liquid, how much force is generated, the buoyancy force is generated, that will be for only partly immersed body. If you go still below, what will happen? The complete volume of the body is immersed. Body, if I tell, it is a solid body. If it is immersed completely, the volume of the liquid displaced by that solid body is more, and more forces will be generated. More buoyancy force will be generated. That all depends on the how much you are submersing for the floating bodies. And if you go for the sinking bodies, once it's try to move just below the water free surface, the forces will remain equal, because all the liquid molecules are surrounded by the volume of the given stone or solid body. And once it starts sinking, the forces which are generated by this total volume of the stone will remain same after sinking or after going below the free surface. But until it is not sinking or until it is not going just below the free surface, then what will happen? The buoyancy force will be changing. The magnitude of the buoyancy force will be changing because of the change in volume of the liquid displaced, or change in the volume of the body which is moving inside the liquid. Okay. So here we have taken now difference of forces to find volume of the stone or force due to that volume of the stone, what is immersed inside the liquid. So to find that, as I told, the difference of these two volumes, ABCFE and ADCFE, if you see, the difference of these two volumes, the total volume, the dashed line, and the stone bottom surface, and this dashed line, if you see, this becomes the total volume minus AD, the top surface of the stone, and volume of this entire fluid upside. If you see, effectively the remaining volume is what? ABCD only. It is nothing but the stone. So that weight into volume they have taken for the force. So here FB equal to what they have written? They have taken FB equal to weight into volume of the stone itself. So body means solid body, ABCD. So whenever, if the buoyancy force is equal to weight, I told you, if the buoyancy force is equal to weight of the given bodies, it will just float on the surface with submerged. Means free surface of the water is in line with the top surface of the body. For floating bodies, okay, for the floating bodies, FB should be little bit more. The buoyancy force should be little bit more than the weight of the body. Then it will float above the free surface, so that part of the body is submerged because of the weight. Part of the body, solid body, will be floating or in the air. So examples, if you see, examples here we have taken a ship. The ship body, if you see, the total volume of the liquid displaced is ABCD. So volume of the liquid dissipates center. If you see that liquid center, if you see, this is the buoyancy point, and force due to which it is acting is Fp. If this force is more, the body can float. If the force due to buoyancy is less than the weight of the ship itself, then ship will sink. Yes or no? Similarly, other bodies are taken. Some parachute is taken in the air. So in the air, both should be in the same vertical line. That's for stable. Unstable we'll look into later. But how much volume of liquid is displaced, that force of buoyancy, how much it is applied, that force of buoyancy should be more. So in the air, if you see the parachute here, parachute will be having a big volume of, or area of the surface to take the air here, inside here, and whatever the atmospheric air is generating the buoyancy force, because atmospheric air is also a fluid. And if that buoyancy force is more than the total weight of the parachute, then it can float in the atmosphere. And to reduce that buoyancy force, what they are doing, they are changing the density of this air later, so that weight of the parachute will be increased and the buoyancy force will be reduced by changing the density of the air. So that what they will do, they will keep on changing the temperature of the gases or the atmospheric air. So once they start heating up, what will happen? The atmospheric air density will lose, buoyancy force also reduces. It can come down. If they stop heating the atmospheric air, what will happen? The cold air will be inside the parachute, and that cold air will be having higher density. The buoyancy force will be little bit high, and it can lift the small weights. Compared to parachute, the weights which are applied in the parachute will be less, like that. And for stability, this sketch is shown at the center. For stability, what they have done, stability means it should move properly without any disturbances in the given fluid. For that, both the forces, the weight of the given body and the buoyancy force, both should be in the same vertical line. Then the body will be in the stable condition. If it starts moving, okay, if it starts moving in a clockwise or anti-clockwise movements, then stabilizing these bodies is very difficult. So for stable bodies, always the buoyancy point should be lower than the center of gravity of the given bodies. Then the maximum bodies will be in stable condition without any movements. So that's why the buoyancy force, if you consider, is nothing but what? Here, the buoyancy force, what is applied in the top side, as per the Archimedes principle, it is nothing but the liquid volume, how much it is displaced, and weight of the liquid itself. So weight of the liquid itself, we have taken W. Okay, and for freely suspended bodies, this special case, what we considered is the body is going to remain in this position only, or it is tied for a given string here, and it is trying to keep in a given position itself. For such conditions, what we are doing, we are taking this weight of the body or the weight of the itself is buoyancy force, because both the weights are same. If the weight of the liquid and weight of the body liquid replaced, both are same, then only it is going to balance. Then only it is going to keep on moving in the same position, in the same position or in the same horizontal direction. It is not going to change its position. In such condition, we are taking this total weight as rho g, volume of the liquid replaced, or the volume of the body, how much it is submerged in the liquid. So difficulty is finding the volume of body, how much it is submerged. This is very difficult. But here, finding the how much volume is replaced by the liquid, there we can consider some different methods. I hope you are understanding. How much volume of liquid is displaced is actually easy to find out than the volume of body displacing the liquid, if the dimensions are not given with respect to body. Is that clear? If the dimensions of the body are given, Directly one can understand if it is a completely a standard dimension body or the ship is given, then one can take these dimensions, how much dimension is inside water, that much dimension of liquid is also displaced. That weight of liquid is nothing but the force exerted by that liquid in terms of buoyancy force. So that we can find out by knowing the density, gravitational force and volume. See, again, if you recall the hydrostatic force equation, rho g a h bar, that is nothing but rho g v m only. Means what? Volume. So here what you have taken for buoyancy force, the volume of the liquid displaced or the volume of the body which is inside the liquid. That volume we are speaking about. Rho g v. That gives us force. How much buoyancy force is acting. All of you understood these points? Okay, if you have understood, we'll take one problem now. So we'll try to understand one of the problem today. You can note down this problem. So here we need to find the volume of water displaced and the position of the center of buoyancy for a wooden block width 2 meters and depth is 1.5 meters. Okay. See, wooden block is of standard dimension they have given. It's easy for us to find out the volume. Wooden block width is 2 meters, depth is 1.5 meters. When floats horizontally in water, density of the wooden block is 650 kg per meter cube. See, density of the wood is less than density of water by standard. It will float. Yes or no? So it will float, but to completely submerge inside the liquid, we have to apply some more force. If I apply some more force which will overcome this density, then it will sink. That is one understanding. But here we need to find out the replacement of volume. Whether it floats or no, we know. It will float because of the density variation. But whether how much of volume of liquid is displaced and the position, that is the given question. And whatever the horizontally floating they have mentioned, it is with respect to total length. Total length, by total length, it is floating. Means the wooden block is not vertical, it is horizontal. So please keep in mind, depth is 1.5 meters, width of the wooden block is 2 meters, it's shown in the sketch here. And length, which is in horizontal floating position, is 4 meters. So this is the total volume of the body, total volume of the wooden block. But our concern is how much volume of liquid is displaced. By that, we can find out the center of buoyancy. So dimensions of the block is given, density of the wood is also given. Now we need to find out volume of water, how much it is displaced, volume of water, and position of that buoyancy point. So first we'll go by known values. The known values are what? Volume of the block is 1.5 into 2 into 4 meter cube. So that is around 12 meter cube. And always we have to find out the weight of the given body to the weight of liquid displaced. Is that clear? So weight of the given body is how much? Rho GV if you find out. So volume is 12 meter cube, G is 9.81, density of the body is 650 kg per meter cube. So once you substitute, I can find out total weight of the wooden block. This weight of the wooden block should be less than the force of the buoyancy or buoyancy force. Then only it can float. And with respect to different densities, we are going to equate these two weights. Both weights of the uh, wooden block and weight of the liquid displaced. We are going to equate, and we are finding at what depth the water is displaced or at what depth it is floating. Then we are finding that height. So this weight is equal to weight of the liquid displaced, because for balancing this weight 76,518 Newton or 76.5 kilonewton, same weight of the liquid should be displaced. Then only it can float. If it is not possible to displace by same weight, then it will sink. That is also there. So that what we are doing, weight of the given body is equal to weight of the liquid displaced. If we equate, so rho is different, G may be getting cancelled, whatever. So once you equate both the weights of liquid and weight of the solid body, then I can write volume of the liquid displaced is equal to weight of the body divided by rho G. So earlier it was rho GV of water here. Here it is rho GV of the wooden block. So for that we know the weight of the wooden block. Rho G value of the water is known, and one can find out this total volume of the liquid displaced. As all of you check these values, please use the calculator or at least mobile. The mobile also can just use the calculator. You can tell me the values. So once the volume is known, here all the dimensions are in standard uh, volume because it is having a rectangular block. It is having a proper length, width and height. So only height of liquid is not known from the free surface, but the width and length is same. Width is 2 meters, length is 4 meters. Height of liquid displaced is we don't know. So once you find out the volume of liquid displaced, anyone can find the height. The problem is understood by everyone. Have you understood the problem and what we are finding? Yes, H is 0.975. Okay. Where is H? He is in class but not replying.
Sir, presence.
Yes. Yes, she is saying always yes. Have understood.
Yes, sir.
0.975 meters is the height. Height of what it is? Height of liquid or height of wooden block? That is very important. So coming back to the problem, height of the wooden block, if you try to find out, we know the volume of the liquid displaced. How much is the volume you are getting? 7.8 meter cube. That is nothing but just go back to the sketch here and analyze how to find out the height. Volume of the liquid displaced is 2 meters by 4 meters into H. That H we don't know, but volume we know. The formula for volume for the liquid displaced is V equal to breadth into length into height. We know volume, we know the width 2 meters, we know the length 4 meters, volume also we know, one of the unknown is H. So like that if you find out the H, that H will be V by 2 into 4 is coming around 0.975 meters. See, this value should be written in all the decimal points because the center of buoyancy and center of gravity is very important later in the stability and unstable bodies. Is that clear? So if you write all these decimals, the center of gravity and the center of buoyancy, if any small difference is also there, the body can be balanced in the later stage. If you try to round off here in the buoyancy chapter, if you round off the decimal points and write 1 itself, 1 meter is the height. So later what happens? The stabilizing the body, whatever the answers you find out, it will be very difficult. Because of that answers, one may understand the body is not stable because of the 1 mm change in answers also. The body may not be in stable condition. Is that clear? So now height of liquid which is displaced is around 0.975. Now one can tell what is the center of buoyancy. What is that center of buoyancy? Center of the volume itself. So take half of this value 0.975. You will get the center of buoyancy. Means the buoyancy force is acting at 0.4875 meters from the bottom. So this force of buoyancy all depends on the volume of liquid displaced. And positions depends on the volume and area. Okay, I think all of you understood the problem now. So stop the class here. Next class we'll take some more problems. We'll discuss about the stability of these bodies. We'll discuss about the position of center of buoyancy and center of gravity. By different positions, how the stability and unstable bodies can be worked out and how to find out these locations with the different shapes of the bodies. We'll discuss in the next class. Okay.